Continuing with our previous talk, we're trying to develop methods for constructing new groups from old groups. In the previous talk, we developed the machinery of cosets. For here, we're going to apply that machinery to normal subgroups and quotient groups. So the new construction here is the quotient group. Now, let's recall how cosets work. We'll have a subgroup H in our given group G, the left cosets in G modulo H. To construct these, we're going to fix an X in G. Then we'll have the set X times a subgroup H, which is just all products X times H for H in our subgroup. Then we saw, if we consider all sets of this type, we have a partition of our group. So what does this mean? First, if we take the union over all left cosets, we get back G. If we take any two left cosets, either they're equal or their intersection is disjoint. So that means I can write G as a disjoint union of left cosets. So our picture looks like this. So that means partition. We also saw, if we consider the cardinalities of left cosets, so for any given two of these, the cardinalities will be equal. Now, let's consider situations that occurred in the previous talk. So for the specific example of S3, so here I have the symmetries of an equilateral triangle. We label the vertices 1, 2, and 3. If I took subgroup H equal to E, comma, 1, 2. If I form the left and right cosets, we note that our cosets don't line up. So the left cosets are not equal to the right cosets. Now, the thing to note here, this isn't just a matter of pushing, the element here to the other side. They're not equal. But I also have that this coset here is not equal to this coset here. So somehow when we jump to the other side, the points are being rearranged in a way that we don't even land on another coset. Now, another example we saw, if we take H equal to, so we have E and the 3 cycles. So these were the rotations. Then each left coset is equal to a right coset. And it's going to be the coset where we just push the element to the other side. So this is going to motivate our big definition here. Definition, we'll say a subgroup N in G is called normal, written N triangle G, if and only if, for all X in G, every left coset is equal to the corresponding right coset. Another way to write this, you can push the X to the other side. So I'll have for all X in G, N is equal to X and X inverse. One more time, if I write this just in terms of the elements, so this will be good for checking with specific groups. For all X and G, and for all N and N, we have the Xn, X inverse is an element of N. Now, this operation here we're going to see more of. We call this conjugation by X. For concrete examples, so let's take a look at our normal subgroup in S3. So if I pick the element 1, 2, 3 in here, I conjugate by the element 1, 2. So I multiply this out, I get a 1, 3. The inverse of 1, 2 is itself. Then when we multiply this out, I get 1, 3, 2. So this is not equal to 1, 2, 3, but it is equal to another element of N. Similar manner, I try it with 1, 3. We get 1, 3, 2 again, and again, that's inside of N, and so on until we check every possible conjugation of elements in here. Now, we'll always have 2 normal subgroups for a given group. We have the trivial subgroup, which consists of just the identity, and we'll have the group itself. So I'll leave it to you to check that they're normal. Now, for a large class of normal subgroups, we note G is abelian. If I take any subgroup in G, it's automatically normal. So the abelian property just says we could change the order of the multiplication. So that means x times h is always equal to h times x. And I can carry that over for the subgroup H. So normal. For some abelian examples that we'll return to later, first, we'll have integers under addition. For a subgroup, we'll have integral multiples of n for some n greater than or equal to 2. For a second case, we'll let our group be the rationals under addition, and we'll let our subgroup be equal to the integers. Now, for a general construction that produces a normal subgroup, we can consider the center of the group. So the center is just going to be the set of all x in our group, such that x commutes with every other element in the group. So g times x equals x times g for all g in G. The way we think of this, our group might not be abelian, but for elements in the center, they behave as if they are in an abelian group. Now, if our group's abelian, then the center of our group is the group itself. In the special case of S3, the center is going to be the identity element. And we note the identity element is always going to be in the center. So that's going to help us satisfy the non-empty property for having a subgroup. And for a non-trivial example, we can consider D8 the symmetry group of the square. So if we label the square as so, the center is going to be given by taking the identity element and the product of two disjoint 2 cycles, 1, 3, 2, 4. So that says flip through this axis and then through this axis. That's better known as rotate by 180 degrees. Now, I'll leave it to you to show that we have a subgroup here and that it's normal. Where do quotient groups come in? We have our cosets partitioning our group. There's a multiplication on the group. So we may ask, is there a multiplication on the cosets? It'll turn out that there is, but we have to use a normal subgroup. So if we're thinking in terms of a partition, okay, when I'm using a normal subgroup, okay, our group could be a bag of marbles. Our cosets are just going to be marbles all of one color. So we pile blue marbles, yellow marbles, red marbles. If we have a normal subgroup, it's like magic. We take our pile of yellow marbles, our pile of blue marbles, we multiply, so we smash them together, and then magically we get the pile of green marbles. So we go to another coset. Now, if we're not normal, what happens? Take the pile of yellow marbles, pile of blue marbles, smash them together, and then instead of getting another pile of marbles, they scatter all over the place, and the marbles are going to have all different colors when they scatter. Now, first, let's note a little piece of formalism that's going to be useful for when we do proofs. So the idea is you don't want to be confused when we're multiplying subgroups by other subgroups by elements. So if we have two subsets of our group, H and K, I'm going to define the product of H and K just as take every element in H, take every element in K, and multiply. So if H is a subgroup in G, then H times H is going to be equal to H. So to show that two sets are equal, we show that we have mutual containment. So first, I want to show that H times H is contained in H. Well, if I take an H1 in here and an H2 in there, we multiply. That'll be an H because subgroups are closed on their multiplication. For the other direction, I want to take any element in H and write it as a product of two other elements in H. So to do that, I could just use the identity element, and then we have H is equal to H times the identity. The identity is in our subgroup by definition. So that gives us the other containment, and this is an inequality. Let's suppose we have a normal subgroup N. We'll define G modulo N as the set of all cosets. So we have our cosets, which are sets representing points inside of another set. G as a multiplication. So first thing we can ask, does G modulo n have a multiplication? Well, let's just see what happens if we use the multiplication from G. So we'll take two cosets, xn and yn. We're just going to multiply everything out. So the way you can think of this is, okay, we have x times, okay, we're going to pick arbitrary element from n, times y times another arbitrary element from n. Take the collection over all those choices for n. So we're going to get a set when we do this multiplication. First, I'll group n with y. Okay, we have associativity, so we could drop the parentheses. Because n is normal, we could switch. And then because we have that n times n is equal to n, we wind up with a coset as promised. Now note, if you were told that there was a multiplication here, the product of xn and yn, your first guess would be x times y times n. So this is natural. Now with that, we can push things one step further. We have a multiplication, so do we in fact have a group? The answer is yes. So we'll call this group, okay, G mod n, the quotient or the factor group of G by n. If G is abelian, then G mod n is also abelian. If G were non-abelian, it could turn out that G mod n is abelian, but it might also stay non-abelian. If we want to know something about cardinality of the quotient group, okay, we'll note here our points are just cosets, so we're just counting the number of cosets. So we're going to have our index. If our group is finite, then we're just going to take the number of elements in G, divide by the number of elements in n. Now, for the proof, so I have to show four properties. For the first property, we've already shown that. If I multiply two cosets together, we get another coset. I have room here for the identity, so I'll do this now. For the identity element, we're just going to use, okay, our subgroup n. So that's the identity times the subgroup n. Now, if we multiply a given coset, say xn, by the identity, which is n, I can remove the parentheses, and n times n is n. So that holds when we put the n on this side. On the left side, okay, we have n xn, and we can use normal to make the switch here. So we want to begin with xnn, which is xn. So that shows that the normal subgroup n is the identity element in the quotient group. Property 2, which we showed third, associativity, we essentially inherit from the group G. If we want to show it, then we would take three cosets and then show that if we multiply the first two and then the third, it's the same as if we multiplied the last two and then the first. Here we're just going to use our rule for multiplying cosets. So if I take xn times yn, that's the coset xyn. If we multiply this by zn, well, this is coset times coset, so our rule applies again. So we get xyzn. If we do this to the other side, we get xyzn again, so we have associativity. Finally, closure under inverses. Our natural guess, for the inverse of xn, we should use the coset x inverse n. To show this, we're going to use, okay, our trick. If I want to find the inverse of an element, I just find another element such that when I multiply it by the original element, we get the identity. And then that's going to be our unique inverse. So when I multiply xn by x inverse n, okay, coset times coset, so we use our rule. So I have x inverse n. X inverse is the identity, so we get n, which is going to be the identity for G modulo n. So, closed under inverses. That shows that we have a group. Now, if G were abelian, okay, so that just means xy equals yx for all elements in G. So it just means the order of multiplication doesn't matter. If we multiply two cosets in G mod n, then what do we have? Well, we have xyn. I can reverse the order to get yxn. And then if I work from this step to here, this is just going to be yn times xn. So if G is abelian, then G mod n is also abelian. For concrete examples, okay, we'll take our usual S3. We take the subgroup of rotations. Here we have two cosets, so the order of G mod n is 2. So we have a 2-element group. Those elements, we have n and 1, 2, n. So as a group, what's happening here? You'll note n is just going to be the identity element, so order 1. And if I take 1, 2, n, okay, well that's not the identity element, so its order is greater than 1. And if we multiply it by itself once, okay, we're going to get 1, 2, 1, 2, n. It's going to be en, which is the identity. So this element has order 2. So that's going to be your typical 2-element group. You're going to have an identity element and one other element which has order 2. Another example, so this one should be familiar. We'll take our group to be the integers under addition. We'll fix an n greater than or equal to 2. Our normal subgroup is going to be all integral multiples of n. Here, the number of cosets, okay, the order of z modulo nz. Okay, so it's what I normally call z mod n. That's going to be equal to n, and so we can write these out as so. You'll note here what happens. Whenever we add or subtract any of these cosets, what do? We're going to take the label out in front. We add, subtract like we normally would in the integers, but to get another element with one of these labels, we add or subtract n till we get into that set. This is going to be our usual modular integers. Again, note, if we let n be equal to 2, so we'll have z mod 2 under addition. The two elements that we have, the identity element, which is 0 plus n, and the element 1 plus n. We have our identity element, and for the other element, if we add it to itself once, we're going to have 2 plus n, which is equal to 0 plus n, the identity. So we have the identity element and another element of order 2. For a final example, we'll let our group be the rationals under addition with the normal subgroup given by the integers. Now, the quotient group has infinite order. How do we see that? So how should we think of Q mod z? So if we take the points, okay, rational numbers in the half interval 0, 1, including 0, excluding 1, we can add or subtract any of those points as usual, except if we land outside the interval, we add or subtract multiples of 1 until we wind up back in the interval. So it's an analog to modular integers. Now, if you think about this, okay, we have an interesting situation. Our quotient group Q mod z is infinite, but every element in this group has finite order. So for instance, if we took 2/3, we add it to itself 3 times. So if our rational's in reduced form, we just use the denominator to get the order. If we add 2/3 to itself 3 times, we get the integer 2. And then adding or subtracting multiples of 1 sends that to 0. So 2/3 has order 3. Okay, note here, that's not absolute value as we usually use it. Let's get back to our motivating problem. Our goal is to construct new groups from old groups. For our first method, we look for subgroups. Here, philosophy was pretty clear. We're looking for groups that live inside of other groups. So the question is, what are we really doing with quotient groups? Now, one way to think of this is that when I form a quotient group of our group, we're taking an X-ray. So what we're doing is we're throwing information away to get another group which has less structure in some sense. So for instance, if we took our example of symmetric group on 3 letters with the normal group of rotations, well, what's really happening with each of these cosets? So what's the quality that links all of these elements in the coset together? Well, if we think about what the rotations are doing to our equilateral triangle, each rotation is going to be a symmetry that sends the top to itself. It leaves the top alone, leaves the bottom alone. So we're losing a lot of structure there, but there is a quality that's being preserved. If I consider the coset 1 to n, these are going to be all the elements of the group that switch the top and the bottom. So when I take this x-ray of S3, we're breaking it down into two types of symmetries of this triangle based on whether we flip top to bottom or not.